Right. Okay, it's my great pleasure to introduce Marta Bílková, who's a multiple-time visitor here to Chapman already, but first time you're giving an MPP seminar, I believe. Yes?
Last year I did Galai with MPP
Exactly,
pre-seminar. So,
yeah. Yes, that's right.
Yeah.
Great. So it's wonderful that you, in collaboration with Roman Kuznets, are going to be telling us about epistemic logic of crash failure. Please, go ahead.
Thank you. Thank you, Peter.
Yep.
I mean, you said multiple times, which is actually 3. So this is a talk about multiple valued epistemic logic, which is actually 3 valued. So,
So for Euclid, numbers are multitude of unities. 1 is not a number, but 2 is already a number. So 2 is already a multitude. And so 3 even more.
3 is plenty, right?
Yeah.
I'm not stating my welcome. So, so this is talk about epistemic logics. I will be showing you, I think, 2 today, in like at least 2 different, or I mean, mainly one, semantical framework, and so what. Also, I should say this is ongoing joint work, which I actually joined as the last person. So most of what what I will be saying today, you can find in Ruzu's PhD thesis she defended not such a long time ago. I will be giving you references at the end of the slide. So there's all the details and all the proofs. So this is about epistemic logic. So we are interested in formalizing logical reasoning about knowledge or belief. It would be knowledge for this talk in multi-agent systems, and like the framework, which is like on which this work is based, is given by distributed computation systems. So distributed system is a multi-agent setup. I will be only looking at static snapshots of such systems, so I will ignore the temporal aspect and the information dynamics, which is given by agents sending messages to each other, because I'm only interested in like how knowledge is actually defined, and I mean, how can we reason? So I mean, dynamics and time comes later and just like builds upon these things. So we are thinking about distributed systems, and since distributed systems are simply like kind of multi-agent environment, they have states. So we all know how to reason about states of a computation system, maybe. So we have relational semantics, which is based on like set of global states of the whole system. And from the perspective of agents, we are thinking about that it might be uncertain what is the global state, because the system is distributed. So there's like they can't like always see what's going on everywhere else. And like this uncertainty is simply model they consider possible global states of the system. So if you come from a tradition of modal logic, this would simply be like a possible world semantics, where we have set of possible worlds, and we have for each agent, we are like specifying his uncertainty based on in between which possibilities he cannot distinguish. So it's like I'm giving you subsets of possibilities as your like range of uncertainty. So on these structures, we can interpret knowledge as agent knows something if it's true in all the possibilities he cannot distinguish between. So we know how to do that, but it is sort of based on the global state of the whole system point of view, because I'm sort of logically listing all possible states of the world. So it doesn't really capture very well the local perspective of the agents, which in distributed computation is the thing you want to like visibly have in your semantics. So there's a sort of dual way of looking at this, where instead of using relational structures, you use geometric models of computation. And so dually to Kripke frames, which for us will be simply set with a bunch of equivalence relations on it, you can dually consider simplicial complexes, which are like built upon set of vertices, where the vertices are the local agent states. And the vertices combine into shapes, and the shapes are the global states. And then, so these models have been used before to reason about distributed computation, and we can also use them to interpret knowledge, just like very much like in Kripke frames, because actually these two frameworks are categorially equivalent. So that's all like nice and classical, but like how does my reasoning about knowledge changes when the distributed system is not functioning like ideally, right? So there's like many cases which also we want to consider, and one of them is where some of the agents may not be functioning properly. And so like the case we consider is where some of them fail altogether. So instead of like only having uncertainty about global state of the system and maybe about local states of other agents might also be uncertain who is still functioning out there. And this naturally like leads to considerations like partial epistemic frames, where you just simply do the same thing you did before, only in some possibilities, some agents are not there anymore. So you have to say like how you actually detect that. And like in simplicial complexes, it just means you turn into impure ones. So
what does it mean that an agent does not function properly? What does it mean that an agent does not function properly?
That crashes. Process can crash and stop sending messages. And then there's like cases where the other like processes would know if that happened or not. So they would still consider it possible that message will come. Or it can, I mean, there can be, I think, in cases where one plays a game in a way that you might be uncertain who is still playing, if some agents maybe stop playing altogether. So I mean, we just take this like idealized cases where the agent is fully there or is not there at all. There might be like possibilities in between. They might like malfunction. They might start doing random things. That's also very much interesting, but it can also be like not functioning fully. So maybe some of them like are still computing something, but not really sending all the messages. So like partially they function, partially not. We haven't looked into it yet much, but I think it's also possible to use similar ideas for that. But like for this talk, it's very simple. Either agents are there or they are not there at all. So, I mean, I will just consider possible states of the systems where some agents are dead.
So would that be an example when you write a message to someone and say, tell me if you disagree, and you don't receive any message? You don't really know if the other person doesn't agree or not, or if the other person had some problem and they never received your message.
But this is like, a bit like giving these examples would require to do like the full thing, including the time and sending the messages and like the dynamics. So that would be like but like here I'm just looking at if I take a snapshot of the global system, then the agents only like sort of know like about the other agents who are still there. So it can like if it's like synchronous and like with every block messages come and are sent, then in every snapshot I would get a bunch of messages. There's messages that are not coming, and now, as you said, at that snapshot I don't really know if the agent died, if the drone crashed or was like shut down, or if something else happened. But then in that case, like, what do I do, right? So I mean, what do I know? Do I know the agents are dead, or do I consider like states where they are still there? Yeah. So so it is a case where kind of partial information comes in, and so we can either like look at it. Okay, we have models now where not all the agents have their sort of equivalence relation defined everywhere. So there's a bunch of worlds where the agent is alive, and on that bunch of worlds I have their equivalence relation, and it's empty elsewhere. So we'll just do partial equivalence relations on possibilities, and then the logic changes. So I mean, for those who know model logics, you know that standard epistemic logic, idealized as it is, ends up being the S5. And so this is like its multi-agent version plus some tweak, because we'll also talk about local variables later on. But it's basically S5. So if I switch to partial epistemic frame, I'm using reflexivity. So the fact that the agent is not in a possible world anymore means that they don't really consider any possibilities in that possible world, not even that they are there, because they just cannot consider anything anymore. So so that's what goes. So you will end up having KB for logic, with a bit of strange property that in those worlds where the agent is dead, the agent knows everything. And that comes from the definition of knowledge operator, which I will show you later. Or or you can just say, oh, but like it's not like that, because why would I want like crashed processes to know everything trivially? Maybe I'm not considering other agents being actually alive and knowing contradictions, but if I would, then I cannot distinguish between the two anymore. Maybe I want to say that like that agents know nothing, like because they cannot even consider any possibilities. And in that case, their attitudes are undefined. And then I'm really doing some reasoning, but I have only partially assigned truth and falsity. And I have this third option saying that something is undefined. So this is what we've been doing, and it leads at that one naturally uses three-valued logic, which is one of the cleanest three-valued logics. So there's a few points I want to make. First is like this switch of perspective from global states to local states, and I mean how people who reason epistemically about distributed systems actually do that. And then like what happens with these weird logics when you just reason over impure simply short complexes, either in two-valued or three-valued way. So so first about this switch of perspective, like from global states to local states. So if I look at how epistemic Kripke models are built up, then as I already said, the visible parts of the framework when I draw the pictures are the global states of the system. And so for each agent, I have an equivalence relation on the set of global states, W. And also I just naturally see propositional variables as global because I have just a bunch of atomic letters and I interpret them everywhere. So I'm not thinking about local perspectives of agents much, like they are there, right? But like where?
What does it mean that this variable is true?
Hmm?
What does it mean that this variable is true?
I assign propositional variables, either value true or false in every possible world.
But
So this is how I build possible
I
worlds.
understand that what is a constant that is true, but what is a variable that is true?
It's an atomic proposition. It's how I set up my framework. So I mean, I have Kripke frame. This is simply the structure which depicts the possibilities and how agents can or cannot distinguish between them. And then on this framework, I'm interpreting formulas. And I start with interpreting atomic formulas, and I simply say that in which possible worlds they are true, and in the rest they are false. But I just interpret them globally in every possible world. Right? Because then I need to interpret every formula in every possible world, and I'm only getting true or false. And then if I look at knowledge, then I'm quantifying over the visible part for each agent, over like those possibilities they cannot distinguish between. So, and then I can compute everything. Like, sorry, just need to move my mouse here so I can see what I'm saying. So where are the local agent states actually here? Like the agents are there indexing the equivalence relations, but if you think about it, the agent's local state is like what information the agent has is given by like their uncertainty range, right? So these are really the equivalence classes. So like for each agent, I have W split into equivalence classes, and they are disjoint, right? But for two different agents, they always intersect because the relations are reflexive. It's like in each world, I have every reflexive loop for every agent. And so I can look at those worlds which are in intersection of clusters like ranging over all agents, and those are like possible worlds, like global states composed of local states of agents. And I can force my Kripke model to be such that those are unique, because if there were two, then no agent would be able to distinguish between them, and then I can make an equivalent, so bisimilar model which does the same.
What is the meaning of the fact that two worlds are equivalent for an agent A? What is the meaning behind this concept?
That he cannot distinguish.
And then does it mean that anything about the truth values of the variables at those worlds?
Not of variables unless I start considering local variables, which I will in a moment.
So,
but the epistemic formulas are like for the agent within one cluster, all the knowledge formulas are uniformly either true or false, because the relation is an equivalence relation. So this is just what like pops up from the system. So it's like I know precisely those formulas which are true everywhere in my cluster. And they are like uniformly true there, because if I see the world, then the world sees me and sees every other world in that cluster. So I can't run out of it. So it's really like an information state of an agent.
The equivalence relation is also the accessibility relation.
Yes.
This is the accessibility relation.
It is the accessibility.
This is the accessibility relation was interpreted in
it's
in
like indistinguishability relation. Yeah. So so these are the local states, but they're just not easy to work with if I just all I'm given is the Kripke frame. And so now I switch, so I have the set of these equivalence classes, and I have a relation between any two of them, and the relation is given by having non-empty intersection, which means somehow that these local states of these two agents are part of the same global state or more. And so if I have a set and a relation, I can actually build two simplicial complexes out of it, but in this case, it doesn't matter which one I do. So it's a very old construction by Keck or Getteris, I think, doing the perf. And then this is what's happening here, actually. So, and then you end up with like so you just take these equivalence classes as your vertices, and like your simplicial complex is built upon that. And the simplices are all the equivalence classes which intersect me in a normative way. And then the way the epistemic Kripke frames are set up, you actually end up with a model you would want, but you just have to say this one thing about the Kripke frames, that that if there's two worlds which are distinct on Kripke frame, that there must be one agent who can distinguish between them. And you can always ensure that, but like, and then you just get these simplicial complexes which actually work as epistemic models. So what are they? So I mean, so they are a bit like, or they will become later more like generalized simplicial complexes, because I will not, I will need to specify like a subset of the simplices which I call global states. So I have like set of vertices, I have set of simplices, which is downward closed, and I always consider that it contains the singletons. And I have, I need to specify which of those depict like global states. And what I really want to do is take the maximal faces, facets, but I can maybe include even some subworlds, because in Kripke frame can actually happen. So, so there's some flexibility there, which will become useful later on. And then I have like a chromatic map chi, which assigns agent to every vertex in such a way that for each simplex, like on each vertex, on each simplex, the agents are distinct. And then you just end up with a model where vertices are labeled by agents, like each facet has all the agents in it exactly once, and we just see it as a global state which consists of these local states of its vertices of each. And then I want to evaluate formulas on this structure. So I also need like to evaluate propositional variables first. But like from this point of view, it's really the natural thing to do is to consider variables as belonging to agents' local states rather than the global state, because in distributed system, this is what actually happens. Like agents have their own sets of variables which sort of belong to them, and they know the value of them. So that's a bit different setup, which will become clear in a minute. So I will just consider disjoint sets of variables belonging to agents, instead of having just like one set of global propositional variables. So this is with local variables only. If I want global variables, I might think of environment as agent maybe, but so far I'm not doing that. I will do that later. And so I will just take classical propositional language with negation, disjunction, and all the other connectives are defined with their usual definitions as in classical logic. And I have this one modality K phi, so a bunch of modalities indexed by agents, in fact, and they interpret as agent A knows phi. And I'm interpreting these formulas on global states in my simplicial complex, which for now are the maximum bases, which we call facets. And they are simply, for that I need to assign to each facet a set of variables belonging to the agent who like is actually present in that facet, which for the moment are all of them. And then so the propositional part is interpreted as we would expect. So negation is true means that the formula is false, conjunction is conjunction, and knowledge looks at every other facet of which the current agent is in its intersection. So the facets intersect in set of vertices, which are labeled by agents. So this is like now the sort of accessibility relation of this structure. So I'm just like moving along facets which intersect in the right agent. And so since this relation is equivalence relation on facets, of course, I'm again recovering the model logic S5. The only thing that's actually different here now are the local variables, because I'm also making this extra assumption that since like if I look from the point of view of a local state of an agent, then like its local state is part of all these global states he sort of considers possible, right? So and if the values of the propositional variables are done in the local state, they're actually like uniform everywhere. So agents always know value of their variables. But this is like a natural assumption. Looks weird as an axiom at first, but like this is how it actually works. So part of the local state of an agent is that they know the value of their local variables.
It is not clear which sense the last one is a theorem.
It's not a theorem, it's an extra axiom. It just happens to be true.
Because it seems to me that this is an immediate consequence of the definition of local variables.
Yes, it is.
So it's not a theorem, it's an axiom.
Not a theorem, it's an axiom, but it's
okay.
valid. It's valid on this semantics. So it's just to point out the logic is not S5n, but S5n plus this locality axioms. So a bit of example.
We have a cat here.
Yeah. To look at what happens if we start killing agents, right? So we like to do this Schrödinger's cat example, but it's not quite Schrödinger's cat anymore. So we have three agents, Ellipse, Bob, and the cat. And Bob is like playing a dirty trick on Alice by putting the cat in the box with no device or no like weird, game going on. Just that so Alice cannot see inside, and he tells Alice that this is in fact the Schrödinger's cat experiment he's doing. So Bob and the cat know that cat is not gonna get harmed. She's just in the box. But Alice doesn't know this because Bob has been weird before, so she cannot be too sure if actually there's any danger that cat would die. And just to be safe, Bob secretly monitors if cat is still alive. So we can always know. But also Alice thinks it absurd that actually quantum principles would apply to a cat. So she only considers cat either alive or dead, but she cannot distinguish between these two states of being alive or being dead. So we can see it as a Kripke model up there, where I have two states, X and Y, which A cannot distinguish. So A has the link, and Bob and the cat know, they can distinguish. And the actual world is like the one, it is the Y, where the cat is alive, right? But how do I depict that cat is dead? So before I do that, we can just look at these two models for a while and see how they correspond to each other. So the model below is the simplicial complex, which depicts the same situation.
What is the difference between the 2B and the 2C in this representation?
Well, so far they just know the same thing.
Okay.
So
nothing.
Those are labels of the vertices.
Those are just labels. Those are the agents. And so the links depict the equivalence relation for ABC on the Kripke model upwards.
So from that Kripke model, shouldn't it be like this? Because the cat only has.
No, the cat can actually distinguish, as Bob can. in which, because cat knows she's alive, so
Sorry, the cat knows that she is alive, but does not know that she's not alive.
Sure.
The cat does not know that it's not alive.
I think cats know they're not alive.
Yeah.
When they're not alive.
I don't know, I mean, cats are a bit.
They go to heaven,
right?
so.
But like,
even
later
if-
people have an axiom
I-
that like.
I suppose that I will not
alive.
know that I am dead when I will be dead.
Some people are dead already. They don't know and
They don't know. Exactly.
So how do we get this?
They could
uh,
if they thought in now.
this simplicial model down there, right? So it's of dimension 2 because I have 3 agents. So it consists of triangles. Triangles depict the global states of the system. There are 2 of them, and only A is in the intersection of 2 of them because only A cannot distinguish. Alice is the only who doesn't know what's going on, and cat and dog are having their fun. What's actually going on. But on these pictures, how do I kill the cat now? Like, how do I actually depict that the state X, which is like hypothetical, is like where cat is not there anymore? So, so how do I do it? I just remove the reflexive arrow in X for C. So C is now not present in X, and I have partial epistemic model. But then the effect, of course, is that in X, C knows everything. So the cat suddenly becomes like omniscience, including contradictions, which is how you actually can like detect crashed agents.
No, sorry,
It's
there
bit
is something
extreme.
that I don't understand. So
Yeah.
the 2 triangles then means true and false. So
No,
Dead
that's
and not dead.
that's just not true and false. Like, so far, they are just 2 global states, X and Y.
but what does it mean to eliminate one C and not the other? If C is the same.
Yeah, but like X is one possibility when we are going to kill the cat.
So
And
X
Y is the
is a
possibility
possible
when-
word and Y is another possible word.
Yeah. And now
And the
they
one-
differ because C is not in X, but she is in Y, because she's alive in Y and she's dead in X,
Is
And-
dead in X, is in alive in C,
in Y.
in Y. Okay.
And A still cannot distinguish what happened because she doesn't see inside the box, but Bob was monitoring. So if something really goes wrong, which he didn't intend, and the cat accidentally dies anyway, then I mean, he would know. So it's this model now. And that's the model where I can actually talk about some agents being dead. And so so on simplicial model, it looks like this. So the C vertex in X is gone because the local state of cat in X is not there because the agent is dead. So they don't have a local state in there. But what happens now, right, the simplicial complex becomes impure, which means like I have a maximal phase, which is X, which is not of the same dimension than Y. So that's basically it. And this model is actually, it's pretty simple, but it's the one that we will use during the talk to illustrate certain weird features of the resulting
Marta,
logic.
so far these 2 models are equivalent, like these 2 ways
Yes.
of modeling epistemic logic. Right?
Even those, but one would have to specify some additional properties on the Kripke model so that you actually get equivalence between your simplicial chromatic complexes. And those are like similar to, so on the one where like everybody is alive, it was that if there's 2 distinct worlds, that there's an agent who can distinguish. On this, it would be a bit more subtle, that there has to be an agent who is actually alive in both, who can distinguish or something. So it's like you can allow things. Yeah, but yeah. And so this has been proved before. So it's proof of categorical equivalence of the Kripke proper models and pure simplicial complexes. But they only consider morphisms, which logicians, it's just crap morphisms. They don't consider bounded morphisms. But then you prove that the resulting structures satisfy the same formulas. Then there's a proof where they prove they are bisimilar, something. And then for these impure, there's a proof where they only prove they satisfy the same formulas, but I'm pretty sure one can be a bit more simple than that. I haven't found like proof that would really satisfy needs like for this case, but I would say it's still equivalent as semantics for epistemic logic. And since as far as I can see, a logician would consider naturally the same notion by simulation or isn't on both. So for us, it's probably like really equivalent. So that's like how we model agents which are not there anymore. But so far, I haven't tell you anything about variables. Like this is just frames. Like these two situations, there's no formulas being evaluated much. So what happens when an agent dies? What happens with their local state, right? So I have local variables and I can treat them. So let's assume that A, B, and C each just has one variable, right? And I can sort of like depict the values as belonging to the global state or as belonging to the local state of the agent, like yeah. So and then when I try to kill the agents, so far we were
But
getting.
you cannot have an example a little more festive. Killing, dying. There is no another example that you can use.
Crashing.
One agent is
No, I mean, okay, so
is
let's
nice, another agent, I don't know.
let's assume that in the
Okay,
left
okay.
one,
I'm joking.
C crashes and in the right one, B crashes.
Yeah.
So to be like, the left one was when the cat was dead, and now the right one becomes when Bob is dead because Alice finds out what he was up to. So she got angry and she killed him. So what happens with the local variables? Like if I'm gonna to delete these vertices. So if I treat them as global, I should assign them to other like that remain there. And I mean, if it's like local, then what do I do? Like, do they disappear or do I keep the last known value? As sometimes it's done, but it really requires to leave this like static snapshot picture, and I would really need to consider the whole computation dynamically. Or I can like assign a fixed value 0. I can say, okay, that agent's like nothing is ever true. But it's also a bit weird because like, why would I choose one over the other, right? It's, or I can just say they are undefined. That because the local state is gone now. But when the local state is gone, they really are undefined. But there's still formulas containing those variables, which I have to evaluate. So I'm doing sort of like partial evaluations, or I'm looking at it from a 3 values perspective. So it's like sort of also very old question, like how do we deal with partial evaluations? Like how do we evaluate formulas which contain subformulas which we maybe cannot compute? And cannot compute might mean like it would take too long, but eventually there would be a value, or it might mean the value is untouchable because like what? So, and then the third value, which can read as undefined, I can really treat it as a truth value, let's say. And then in one case, I would consider both the possibilities, like it can be 0 or 1, but I don't know at the moment. And I would end up using strong, clean, deep-valued logic. And in our case, we consider it infectious. So it's like we cannot touch it anymore. And then, like, if I have a direct subformula, my formula which is undefined, and the value is undefined. And it carries the information that somebody on a way of like unraveling the formula is not functioning anymore. So that's might be one explanation why to use this extreme way of interpreting. So, and what happens with knowledge of agents who crashed? Like, so if the local variables become undefined, maybe the epistemic attitude should also become undefined because like they consider no possibilities. So this was the idea that Hans van Titmarsh had that natural way of looking at this really that agents cannot consider any possibilities, so they cannot evaluate epistemic formulas, and therefore they become undefined. If I don't have this three-valued environment, I can still do a lot on the two values, but then I have this effect that agents vacuously know everything. But I mean, if I'm just a mathematician, I think, okay, I mean, it's just the way of syntactically say that the agent is that anyway, so I might not care too much, right?
That's nice, this idea that someone that is dead knows everything.
Yeah, wouldn't that be nice? But like, including contradictions, that's, I think, like a Zen,
Right, everything.
complete
Knows
Zen,
everything.
like everything
Right.
at once,
Yeah.
maybe, I don't know. Yeah, so for this talk, like we will build epistemic logic, which expands this weak lineage logic known as paraconsistent weak lineage logic. Not that they thought that they were doing paraconsistent logic in the first place, because it's almost classical. It's just you don't need to tell people they are actually doing anything non-classical. You just tell them, oh, you just deal with these parts which are undefined in this way. And then you just reason as you would normally. And I will try to explain how that's done. So now how do I choose the three-valued interpretation of the modalities? That's like the question. And so if one thinks about it, so Ka phi says agent A knows phi, and it's dual using the three-valued cleanness negation, which works classically on classical values and is undefined on undefined, right? Gives you a notion of like not knowing the negation, which means that agent A considers phi possible. And so, so if I'm looking from global state, I'm trying to evaluate formula agent A considers phi possible, and I'm saying when I think it would be true, then it's natural to pick, okay, it's true in at least one possibility for the agent, because that's what it should be. But then if I want the knowledge to be its dual, then I get this definition, which says that phi is true in all the possibilities for the whenever it is defined, can also be undefined. So it's undefined or true in all the possibilities. But at the same time, it would be weird if it wasn't true in at least one, because like that would mean that the agent is dead. And then I want to say it's undefined and not true. So it's like, but true in also at least one possibility. Anyway, people who have some experience with these things, like, see, this is not like how normally you define box or diamond modalities. Like the diamond looks okay, but a box is not really given by a meet or by universal quantifier from big clean logic. I find that kind of interesting, but what it does, it leaves the validity, because in this logic, being valid means I'm true whenever I'm defined. So this is what it actually says, like it's valid in all the possibilities which the agent considers possible. So this is the semantics, and so it's a kind of like you have two options. You can just look at it, okay, I'm now doing this evaluations in a three-valued algebraic structure, then the definition would look a bit differently. Or you can really split the definability conditions from the truth conditions. And then it looks more like people are sort of used to. So you say that local variables of A are undefined exactly in the cases where A is actually there, which in impure simplicial complex means he is alive. And then it's infectious, so like it's the formula is defined if and only if all the direct subformulas are defined. But with the modality, we actually, what we want to say is that the epistemic attitude is defined when actually A considers at least some possibility where the subformula is defined. Because like otherwise I don't even want to start considering the formula is null. So, and then the truth part is pretty much as you would expect. There's always the definability assumption. Only in some cases we can actually skip it. So we say that formula is true if it's defined and something standard holds. So this is depicted here. So like knowledge of phi for A is true if it's defined. So at least there's some possibility where it's defined. And then whenever defined, true. So that makes sense, epistemically speaking, but it's a bit non-standard also. Yeah, I would say, because I haven't seen it really anywhere else. And then, like, what does it mean for a formula to be valid? I mean, like on a model or class of models or class of frames, it always means true whenever defined, which means undefined or true. So on the algebra of 3 values, we are picking the truth and undefined as designated. And then it sort of messes up how the logic works as a consequence relation, because it's not trivial, not even on the propositional part, but then we know how to.
Why can you skip the definability for the it?
I would say by induction one just.
By induction.
Yeah.
Because
you can,
because
yeah.
if you accept the
I know.
of the others,
okay.
then
No, I don't know. I think like you can put it
yes,
anywhere. That's not so. Things that go maybe wrong or not completely wrong, but sort of strange, is that it looks like a pretty much normal model logic, but like the axiom K is not valid. So why would I think that the axiom K is somehow important? Because it says something about knowledge of agents to be close under those Ponens rule. But people who ever saw like weak clinic logic know that modus ponens is not universally sound there. So we are not surprised that this will sort of affect also this axiom, but it's interesting that this little model is kind of, again, like showing me why, or I mean, where it can go wrong. And it can go wrong because now I have a place where, so I mean, I'm looking at a formula that A knows that PC implies PB. And so if I look here, then yeah, PB is true everywhere where C is true, where A can C, right? But it's not defined wherever like the other is defined. So what goes wrong is that PB is defined somewhere where PC is not defined. And then what to take from this example is that that we sort of have to trace definability consequence and truth consequence at the same time.
So, I have a question about how like one situation kind of works here. Like if there are like me and then 3 other agents, and I know that this, if there's some fact, I know this agent will tell that agent, and I know that this agent will tell this agent. And now those implications in that knowledge are kind of, if everything's defined right, that happens. Can I still like get something where I know agent 1 will tell agent 3? Like if agent 1 knows something, it will pass it on to agent 3? Because the middle one could be undefined.
Yeah. So that would be more for the dynamic part of the picture, when we actually like see how the knowledge changes when people send messages.
It doesn't have to
That
be
would affect.
dynamic.
You mean like nesting of modalities now, or?
Yeah, yeah.
Yeah.
It can just be like,
Yeah,
I know
yeah,
that
yeah.
knowledge at
Okay.
A implies knowledge at B, and I know knowledge at B implies knowledge at
Yes.
C.
Yes,
Can I
then
combine those?
it will become undefined, like it will become undefined.
So that whole implication will become undefined?
I cannot use the transitivity rule fully because the modus ponens is not fully valid here. I will show the like axiomatization. So I will, yeah, now I see what you're asking, but it's kind of similar phenomenon as here. So that's the axiomatization. And so on the top, I've defined like what we mean by definability consequence. So it's simple, like define on the global states that like you would define truth, consequence only. Now it's for definability. So it says that whenever all formulas from gamma are defined, psi has to be defined too. And then you just write down the axiomatization, which pretty much looks like classical S5. And some of the things happen to have side conditions on the definability consequence. So I still use all propositional tautologies as axioms. I have like the S5 logic with necessitation rule. Necessitation rule preserves validity, not true validity. And then I have side conditions with the modus ponens rule, which sort of partially would answer your question. So I can only detach phi from the phi implies psi when both are like valid, but also whenever psi is defined, phi is defined. So I cannot exactly do these like transitive transitivity of implication rule when the middle guy is undefined, because that would violate like one of those. And so also a little bit more involved definability condition pops up with the K axiom.
Sorry.
Yeah.
I do not understand no, come back, the N condition.
It's not condition, it's a necessitation rule. So from phi being valid, you infer that agent A knows phi is valid. Valid now means undefined or true.
So phi does not mean phi is true. It means phi
It
is
means phi is true whenever it is defined.
okay.
That's the trick.
I'm a little confused about the little triangle on sideways.
Yeah.
Like the definition's on top, and it says like for all phi, it's defined at X means that it's defined at C, or that top definition.
Yeah, it means that so gamma definability entails phi if so if all formulas from gamma are defined, then phi is defined, and it's like what's psi? Sorry. So it's like in every facet where all formulas from gamma are defined, psi has to be defined too.
Is that like a, can that be interpreted syntactically, or does
Yes.
it make sense in this?
Yes. So so let me comment first a bit like on the, so if you just look, if you ignore the modalities, it's just classical tautologies plus the rule MP, then you get a paraconsistent weak Kleene axiomatics. So it already has this modus ponens rule with the side condition, and so sort of also explains why the logic is paraconsistent, because even if I had constant for bottom, phi implies bottom, and phi wouldn't really infer bottom, because bottom is always defined and phi might not be, because bottom contains no variables, so I cannot make it undefined. That's like
This is
one of the explanations.
yeah, the definability
Is
for the paraconsistent
Yeah.
weak Kleene can be expressed in terms of some
Yes.
variables of a formula are included in the variables of the other.
it's variable inclusion from phi to psi, so
From
it
phi to
goes
psi.
like
Psi.
definability consequence is a converse of variable inclusion on the propositional part.
Yes.
But since the definability conditions from the modalities are now modalized, then this also becomes a bit more like involved. So it's not just variable include, but you can actually decide it. So you can have like it's characterized by certain properties. So if I'm looking at phi is like definably entails psi, I can turn both of the formulas like into kind of three structures, which are like syntactic trees just labeled by agents in a certain way, which sort of code the minimal requirements for this formula to be defined on a simplicial complex. So it's like, it would be like embeddability between syntactic trees of formulas, which is like modelized variable inclusion, in fact. But like we have a way of doing this. So this axiomatics actually makes sense because the side conditions I can treat syntactically. So it's like, and it's not even.
Can I also ask what the K hat means?
What?
The K with the little hat on it.
Oh, that's the diamond.
Oh,
That's the.
okay.
So because I'm not exactly normal anymore, because I have the limited K axiom, I also need to include like it for the diamond modality, which normally in S5 would be provable, but here I would need, I don't know what exactly I would need, something that I cannot use, maybe transitivity, which I cannot use fully. So that's a complete axiomatization, and there's maybe like let's look at the axioms, because like this logic is non-classical, but I'm including all the classical logic there, but the rule, right? But then like how does it work? So what's weird here?
Yeah, I have a question is that, you said this is the axiomatization, but in the axiomatization, there is those clauses to be definable, those depends on semantic.
We can.
But you said, I just wanted to emphasize that
Yes.
it looks like it depends on semantics, but can be expressed
It
without.
can be expressed
semantics.
using sort of simple conditions on what we call life trees for formulas, which are bounding the size of the formula, and like you can just check whether they embed into each other. That's how it works. If one looks, for example, at the T axiom, which in epistemic logic is often called factivity or truth, because it says that whatever is known must be true, it doesn't quite say that here. Because like, okay, so this is an axiom, so it's either true or undefined everywhere. But I mean, it can be undefined. There might be situations where A is dead, and the whole formula is undefined. But like, whenever Ka of phi is actually true, then phi cannot be false. But it's not like, it's not really saying what it says classically. So that's what I'm saying. It looks like the classical S5, modulo some side conditions, which one might be tempted to avoid, but also the part which doesn't have side conditions actually means something a little bit different, because now I'm reading this in a three-value context. So it's not, some people would like object that this is not factivity axiom, and then it's not what you would want for this to be called knowledge, and we shouldn't call it knowledge. That's like, we got these comments.
Yeah, I had a question about axiom L, so the local. So
Yeah.
that's also something that would be, so it could be undefined if A is dead, right?
Yep.
That's the only case in which it's going to be undefined.
Yes, it's the only case when it's going to be undefined. Yes.
So you still want to say that when an agent has crashed, it's undefined that they know their local variables. You don't want to say that they don't know them anymore.
Yeah. Wait, radical. So yeah, this is all nice. So that's the point where I actually came into this topic. They were like showing me what's been done, and this like interesting, but we noticed this one thing, like you cannot like really deal very well with bisimulation. So what are the bisimulation? Like expressivity for this logic, and I was like saying, okay, it's just partial Kripke frames, so we know what bisimulations are, and we are in the three-value logic, so we know what bisimulations are. And then, okay, so yes, we know what the bisimulations are, exactly what you would expect, where you would just require in two bisimilar facets the values of all atoms being the same in the sense of three values. So undefined whenever undefined, true whenever true, false. And then it just the usual zigzag pattern of Kripke frame bisimulation. It's really that. So the language is invariant that we would expect maybe, but it's not expressive. And like the failure is kind of subtle, but also, I mean, immediately tells you what is wrong. And it's like, again, the same example, like this model with this world where C is dead, which is not on the second model. When I look at Y and Y prime, they satisfy the same formulas in my language, but they are not bisimilar because I cannot map the X anywhere. So I could try to map it into like a subworld of Y prime, but it also wouldn't work. And like, okay, and then there's like more examples which are more involved and go to any kind of depth where it always can be like, you can make this point that it goes wrong somewhere. But like, what is the reason that this goes wrong? Like, because in the left-hand model, A actually doesn't know if C is alive, but there's no formula that would say so. Because there's no formula that would say that C is dead. And one might be tempted to use somehow the local variables, but then it wouldn't quite do the job. So really there's something missing in the language. And that's to talk about agents being alive and dead. And so what one can do is to just like look at what would be like the minimal or a minimal way of like what to add so that we can recover an essay. Milner, actually you can just add global variables for agents being alive or dead. So for each agent, I would have a letter. So for A, I would just lazily use A again. And I would have like atomic formula A and its negation. It would be defined everywhere. And it would just depict the set of worlds where A is alive and the complement would be A. So this is like one way of doing it, and you recover like expressivity. And it seems a bit like we haven't done much, because like another idea would of course to have like constants for the truth value, so something a bit more radical, because we often like we see that it in many valued cases it recovers an Milner property. If I can say formula is undefined here with a formula, then I am fine. But it's not actually the same thing that we did. So even with the global atoms for alive or dead, I cannot uniformly express phi's undefined with the true formula. But I can do it depending on a concrete model. And that's what saves the Milner property, because I always get my distinguishing formulas where I need them, which are actually true here and false here. But it's not like equi-expressive with these variants of paraconsistent weak linear where we actually have constants for truth values, for example. So it's an interesting version of like how to get something more expressive, but not quite the same thing. This is the weaker way. I can express agents being dead if I had the constants. But what happens with logic? So I'm adding these new global variables now, which are defined everywhere. So they really sort of belong to the global states. And they are true exactly when A is alive in the facet. So the logic actually changes quite a bit, because in a sense now, because I can talk about agents being alive and dead, I also have to include axioms saying things like there's at least one alive agent, or if there's only one agent alive, he knows everything, or that agents actually know they are alive. It's like Descartes' axiom. So the logic ends up being like a bit of expansion of the previous one, but now it's a bit convenient to sort of make a bit like also subtle expansion to the definability consequence relation, and that that affects like the completeness and the deduction theorem that one can then prove, which I wasn't able to prove without it. And it's sort of like define up like a consequence which traces at the same time like non-falsity and definability. So what it says is I have this like extra sort of assumptions, and then I have that phi when phi is defined and psi is defined, almost like I had before. And it also can be a set of formulas here, and this extra set means that I also assume that like things in gamma are not false, which means true, or undefined, which means like valid. So if I keep gamma valid as I'm going along facets, then whenever phi is defined and psi is defined. And then like I decorate modus ponens with this condition instead. Like it's a bit more subtle. In the PhD thesis and like there's like two variants of the definability consequence, the one we had before, and then like the big one, which says if phi is true, then psi is defined. And this is just packing them sort of in one, and it saves you one axiom. So now this is just like a slight change. So there's this new Descartes axiom saying that agent A knows they are alive. And there's like a non-emptiness, that there's at least one agent. And this weird thing that if there's only one agent, they know like everything. And this is also what the people who are thinking about impure simplicial complexes in a two-valued sense, with this effect that agents know everything, they are also considering the same bunch of axioms. So it's really the same logic, only it's like paraconsistent with the variant. And so so that's the two logics. So there was like, if I switch from global states to local perspectives, and I only use local variables, and I do everything in paraconsistent with clean, I'm not expressive enough. So we added these global variables. Now we think it's also usually good to have like both. And so I will comment a bit on these two logics in a minute.
I feel like there should be intuitively to me, there should be an axiom that says if A is alive, then any proposition that belongs to A is defined. But I don't think you have something. Is that provable in the system, or is that just something we don't want?
It would be like how you would express it. Like A implies PA or not PA is true anyway, because PA or not PA is true because it's a classical axiom. It can also be undefined, but it's like valid. So I cannot like really, this is like the thing. It's not, I'm not like, if I was axiomatizing a set of formulas which are always true, it would be a different task. I'm only axiomatizing those which are true whenever defined. So the expressivity issue is a bit more subtle there. So there's really no need to say that, I think.
Something's always defined if the agent is alive.
Yeah, the agent A could
Yeah.
hear propositions involving KB, some other agent.
Yeah, I just.
And that other agent might not be alive. So
Yeah,
Right.
it gets interesting when agents think about knowledge of other agents.
So I was restricting it to just the propositions A knows, like the PAs that belong to A.
Yeah.
Like if A is alive, then those have to be defined with like the little thinking on top. Pointy infinity.
So it would be like A is alive, then a fragment of the language that only involves A's own modality. Which is S4.
No, I think you're thinking of the local variables, right?
Just local
The
variables.
local variables of A.
So like a little bit weaker than that.
Yeah, but
Even
like,
weaker than what I said, yeah.
like saying that local variables of A are defined, I say that saying A is alive, but that's like the thing I'm saying.
Okay.
And that's it. It's like A is for it's just
I guess I'd want
Yeah.
an agent to be able to know A is alive and then reason, like if they have that information.
like agent A knows that B is alive, but that would entail something.
Then you could like work with those A propositions like purely classically.
Yeah.
Instead of.
Yeah, that's interesting that I can always make assumptions. Okay, this subset of agents is defined. And then this fragment language and I can work with plus. For all these. Yeah. So it's surprising how this slight expansion of the actually complicates the completeness proof. Also had really like a lot of fun, like doing the completeness proof. So what can we say about these two logics? And some of it is still conjectures, which some of them are like of the form we are writing down the proofs, but if we cannot claim because the proofs aren't there yet. And some of them are like, okay, we know what to do, but that like hasn't been done yet. So what's done in the PhD thesis of Bruto is like the weak completeness proofs. So we know both the logics are complete. I think it can be turned into like finite model property proofs. And then we would know they are decidable, we think they are decidable. We don't know that. Can be also one, but I don't think so. No, we cannot because it's multi-agent. Yeah. Yeah, so I mean, one of my questions also was like, what happens with a strong completeness? Like, what happens if I look, because it's a model logic, it has the local consequence and the global one, which runs over models, right? Not like over facets in models. So like, what happens there? What's the deduction theorem? Because like, I'm proving that necessitation rule. So do I have some form of deduction theorem? And it's all kind of like untouched. So yeah, so we have a deduction theorem, which is pretty much the S5 deduction theorem, only with like a definability condition, because you cannot always do it like go in there and back with phi, only if like the assumptions whenever they are valid and like psi is defined and the deductive term is defined too. And the deductive term is not quite like in S5 because the logic is not quite normal. So you would just start with the proof of psi from phi, and you would trace the necessitation instances and comments instances. It give you a combination of nesting boxes and conjunctions, but you cannot always distribute because that requires the K axiom, and that's not always there. So it's a bit like ugly deduction term, but like if uglier than in S5. Because in S5, it would simply be sequences of agent knowledge modalities in contraction. But it is like it has a deduction theorem. Also, I can prove like it is both of the logics are complete, simply building a canonical model on 3-valued valuations. But it requires this tracing this kind of definability consequence along the way. And then what I would really like to see, because we know about classical logic and paraconsistent weak cleaning. Paraconsistent weak cleaning is a variable inclusion variant of classical logic. So consequence in paraconsistent weak cleaning is exactly the consequence of classical logic intersected with variable inclusion. So variable inclusion is actually the definability consequence propositionally. So my question is, and I think the answer is yes, but I mean, I haven't proven it yet completely, is that these things are actually like sort of naturally relate to the 2-valued S5-ish logics in a similar way. So, but like now using the definability mixed consequence, which appears here. Which would also like be an argument maybe a little bit in favor that you can like, it's like almost doing multi-agent S5. And everything works fine. Yeah, that's still like proof theory and decidability and things like that haven't been done, but we now have a kind of nice calculus for multi-agent S5, which I think we can work with and try to see if it also works with the undefined or with the site condition, and then see what we can with her. So that's it. There's some references like the second paper and the papers that it sort of refers to. It's like people around Reisbaum and who both have done lots of work on epistemic logic for sequential complexes, including this two-valued perspective on the case with faulty agents, which relates directly to our three-valued perspective. And these are like the previous work of the team of co-authors, which was using. Thank you.
Is there any question for Marta? Yes.
So going back to this kind of similar property
Yeah.
that you couldn't get with the original logic. So
Yeah.
If you, instead of having like a global variable for every agent, you just have a global variable for truth, like for you know, verum and falsum. And then you say, in this case, like
Constance.
yeah, right. So like Alice, in one case, Alice knows that the cat knows verum, in the other, she doesn't know that. Does that help, or is it?
Yeah, I think even if I just add this like classicality operator, like I have a classical truth value, then I would already pick out classical, but it's a bit stronger. Like it's almost like having constants for all the truth values. That always helps. But if I don't want to do it, this is a way of, and I think it's weaker. Like if I had all the constants, I could talk about that and the live agents. I could, for example, say that the local variable is classical, right? And then I know that the agents lie. But here, if I have just these global atoms for agents, I cannot actually express the value undefined in this way. I cannot find a formula which, like a term in my language, which for phi would be true exactly in facets where phi is undefined, only based on phi. So that would be the two languages then would be like expressive. So that I cannot do, and we can prove that we cannot do it. But we can do it based on a model. So it's like for every two models which don't agree on phi, I can find a distinguishing formula, but I cannot do it like uniformly. So that's what makes an SML work.
Do you have a sense? Sorry, do you have a sense of an axiomatization for that logic that would have, you know, constants, and if it would be simpler than?
Yeah, we can, I think, directly translate. I don't know if anything would get simpler. I don't think so, because even like the two-valued one is not really that much simpler. So there's the same axioms, only like not with side conditions.
I know Ben has a question, but there is also a question in the chat. Can we just check for a second?
Let me see if I can see the chat. Okay, constants are expressible via global variables. I don't believe
cannot
that.
read.
I don't believe that. Yeah.
There was another comment.
I mean, like,
There are two comments.
okay, so constants bottom and top are, but the undefined is not. So, okay. And there's comment, thanks Marta for the talk like in Brazil. Yeah. So like bottom and top. So I mean, if I have, when I have global atoms, then I can express a proposition which is always true, always false, but that's it.
Oh, but I guess my question was whether you actually just need that top and bottom to get the Hennessy-Miller, or
No, no, there's like in NSA Miller, if I have two states which are not bisimilar, I'm looking for a distinguishing formula.
Right.
So I look at all states which relate to them and inductively assume that I would have distinguishing formulas there because there's this one pattern which is not matched. So I can distinguish like one step deeper, right? But if that thing I can distinguish with formula which is undefined here and true here, then I need a formula like, I mean, to put it back to the world where I started, I actually need to turn it into a formula which was like true here and false here. Otherwise, it doesn't work with my connectives. It's also like interplay with connectives and the modality and the definitions I was picking that I would really need this. And then I would have to, for the undefined, I would have to turn it into true somehow. And that just with having top and bottom, I cannot.
so, okay, so just to make sure that I understand that
Because they always do.
you have this like this hierarchy of logics, and it's supposed to be strict, right? You have the one without any global variables, the one where you add top and bottom, the one where you add
Oh, okay.
the agents,
Yeah.
and then one in which you add top, bottom, and
I guess, yeah.
okay,
And then I would have to think about it, whether I can distinguish it, right? Yeah, I will think about. I think yes.
yeah, that's your conjecture.
Yeah.
Ben and then Spencer.
Okay.
So necessitation is an axiom. It only applies to valid formulas. Is that right?
Yes, it's a rule.
Okay.
Which only applies, yeah. Applies valid and
So that means logical omniscience. Philosophers follow that.
yes. The
But-
logic is based on this like idea of knowledge which already has all the bad properties in the first place. So
And if you have omniscience, this avoids a problem that I've thought about for a long time due to Frederick Fitch, having to do with knowledge. But you don't have something, so you don't have omniscience for contingencies. So have you not even, I guess my question is, we can talk about the Fitch and everything that's down the road, but have you thought about contingencies? Do you recognize them? Do you want to add them? Where?
I'm even thinking if the omniscience here means what it usually means, because if the epistemic attitudes also might be undefined. So if I say, okay, like knowledge of something is a valid formula, doesn't mean because like dead agents don't know it, right? So like the dead agents like basically have it all undefined. And then so if it involves something on the way, some agent which is not there anymore, then I cannot really like use it as a knowledge because it becomes undefined for me, so that I cannot sort of detach phi from it because I have the T axiom, but I cannot use the modus ponens. You see what I mean? Like I have like knowledge of something, but I cannot get at that something because somebody on the way is dead. And then, I mean, I cannot really detach. So if like, is it omniscient? Does it mean that I really like know it? Or because then my knowledge becomes undefined too? And then, I mean, yeah.
But so if you can never really have omniscience, then maybe, I mean, this might be.
Well, not never, but but it's a bit more subtle here, because the necessitation is really not doing what it does in the classical logic here.
Okay.
Yeah.
Thank you.
Yeah, I guess I'm still a little bit confused about the eliminator of the propositions that an agent is alive. Like if I'm picturing a model where like one agent's epistemic spot is like a point, right? And then every simplex or maximal simplex off of this point contains a possible epistemic state of a certain other agent. Then it should be like, because that means every possible world or every world this agent thinks is possible has that other agent alive in it. So I feel like once you know that, once this agent knows that that other agent is alive in every possible world, I feel like that will affect how they reason through this. Like they would know that this agent can be counted on, kind of.
Yeah, I mean, it's also like the thing here, like since A couldn't, like A would sort of like consider it possible that C is dead in this model, but he has no formula for it. So it's like you would need to, that's like the thing. And then like with the global variables, you can trace this.
The 1B spot right there.
Yeah.
Or the one on the right.
Yes.
Then the blue guy knows that the other two agents are alive.
Yes.
Because that's the only possible.
Like here in Y prime. So in Y, yes, in Y, yes, not in X.
Yeah, so
Like two different local states for B.
so blue at that local state, because each agent knows their local state, essentially. B knows that the other two agents are alive,
Yes.
and then can like know that if one knows something, they'll tell, or one's knowledge behaves classically, or so I guess I'm just concerned about
Yeah.
like, is there a completeness theorem for this over these models? Like for the logic
Yes.
right now, it's complete.
Like the, yeah. Like both of the logics I presented are complete.
Okay.
That's not the problem. They're just not like one is not expressive much. So Roman says on the point of constants, each agent still is logically omniscient with respect to its own local variables, which is like part of the what two of you were sort of after, because they like already know the values of all their variables, so they can of course like so. But it's making a different point. It was like more that really the rules and the axioms do not preserve truth here, but truth wherever defined. So it's giving you a bit like weaker closure properties than one is normally considering. That was the
What did you just quote?
Mike Walter, who knows these things because you did these things. So oh yeah.
What is the eliminator for those? What is the eliminator for those something is alive terms? Because
eliminate what you
like if you know another agent is alive, like what can you prove from that? Because in the list of rules, there was no way to like use that as a premise to get other things. It was kind of where I felt like the block was.
yeah. See a bit what do you mean? Well, there was like one, right? It was this weird one when there's only one agent alive. So it sort of uses this assumption. Well, I was more like wondering if one can actually do a bit more about describing the definability consequence using the global atoms. We were just looking at the kind of syntactic description of it, like I have my two formulas, how do I check?
It's like
But can I actually, because like I'm also interested in algebra as this logic, right? And I would need that. So now I'm wondering if my language would that would also be connected to.
I'm just thinking about theorems of the form like A implies
Yes.
the K rule about KA or something like that.
Yeah.
I guess I don't see how you get that. That would be valid in all models, but
I think, yeah, like some instances where, I mean, if I look at the K axiom, right, then it requires some definability tracing here. So if I just, as phi and psi, if I just put local variables of other agents, I can describe this a little bit here, maybe. But like it's more like the global atoms tell me they're always defined. They don't really talk about definability, they only talk about truth. But like if they are true, then something else becomes defined. So they appear in the definability makes consequence here. So if A is alive, then PA is defined, for example. So I can like form like things like that.
Okay, so there is a rule about like A being alive, meaning.
That, I mean, if I was axiomatizing this definability consequence up here, then yeah, then I would use rules like that. Now I was wondering if I can actually turn it into a formula or something.
So, yeah, it goes
And I
into the.
don't see that so far, but
So this accessibility relation on this slide is. More goes into it because that's to take into account what's provably alive. Is that still like a computable, decidable relation?
I mean, yeah, if gamma is finite, of course, then yeah. Yeah,
It's finite, right?
yeah. In principle, when I'm proving strong completeness, I wouldn't assume that, right? But like proofs are finite, so and since I'm only using it in proofs as like set of assumptions, I would consider gamma be finite here. Then yeah, then I can. Yeah, but then this becomes a bit of like semantic condition. So one would have to. We still have to look at this.
Yeah,
This is
replace-
pretty new because we were simplifying there was extra rule in the axiomatization, which is in the PhD thesis of Ruzo, and then like to get rid of that rule because we felt it might not be necessary, but it popped up during the completeness proof. So then we sort of cleaned up the thing, but this thing we don't really have this like pre-embeddability description because there's the extra assumption of formulas in gamma being non-false, and it's not
It
really.
seems kind of non-trivial.
Yeah, it seems.
By induction.
It
Like
seems.
instruction.
But strangely, in the completeness proof, you needed to trace definability also on the assumption of something else being true. And tells me that it's not like completely obsolete.
Peter has a question. Sorry.
Oh, I was wondering if are there some type of epistemological puzzles, like if you have several, or if you have enough agents, then together they can figure something out. Do you need to? I mean, I'm thinking of something like the muddy children puzzle, but
Oh, that would be nice. That would be a question for Hans. Hans would be the person who have thought of it.
yeah, I can't come up with something right now. I was also wondering, is this logic decidable with
Conjecture it is.
even with multiple agents?
Yeah. Like, I mean, my conjecture it is sort of definability consequence variant of S5. And then depending on how hard it is to decide a definability consequence, that would like, because like multi-agent S5 is based complete, so that just but with the local variables, I think would be easier, but with these global, like it's the consequence, like the definability consequence becomes more involved. And then conjecture, yes. Don't have a proof.
Other questions?
What's the complement of, sorry, the dual of knowledge? Is it like entertainability? You could think
Considering
about
it possible, it's like not knowing negation. And pretty much negation, you still think about it pretty much classically because like undefined things that just stays undefined. But like whenever defined, it behaves classically. So it's still, I would read it as not knowing, not phi, as considering phi possible. And the interpretation literally says that. Like the agent considers it possible that phi is true.
Sorry,
Comments? Alan,
very good.
I said things. And I answered wrong.
Okay, thank you.
Fast one.
A very general question. Classically, knowledge is intended to have at least, so to say, three dimension. Determination of truth, and here I see where truth is. But there's also justification,
Yes.
and there is also opinion. No, there is the three-party definition of knowledge. Then you can add something more, but the three things should be there. So it seems to me that here the accessibility relation is doing too much work, because you use them to mimic both justification and opinion.
Yes.
And so, classically speaking, opinion and justification are very different things.
Yes.
I can have opinions that are not justified.
Yeah.
So it seems to me that there is a dimension of knowledge that is missing here.
Yeah, there is. There would be like interesting to like not start with the classical S5-ish approach, like no questions asked, and like making it into a. I mean, it is a bit like restricted setup, because you're just working with distributed systems, and they are like way more restricted and like reasoning of human agents and social contexts. But still, I think it would be nice to sort of trace these things.
Ooh.
Like to see what it would mean for like agents of distributed system to have justification for their knowledge. Like maybe, yeah. Like they don't really act much, right? They have their protocol, they run and they receive messages and they send messages. So it's really like kind of, they are not making decisions or doing things or thinking or reasoning really. It's a bit of stretch, but so this is all kind of implicit knowledge, I think. But it would be interesting for me, it would be interesting to know if somebody considered like reasoning in social complexes, distributed system, if it makes sense at all. And then like how we would deal with justified knowledge.
So here is that they do not believe anything for which they are not justified. Is that it?
It depends.
They only
It
believe the
depends
things that
how
are-
you interpret the accessibility relation.
Yeah.
It seems to me that the most reasonable way is to interpret it as justification. So
Yeah. And then
I-
here they only believe the
but
things for
then
which
there is
they are
no more
justified.
opinion. There is no more belief.
They only create a belief when they are
Exactly.
justified.
That is the point. So you project the belief on the justification. But
but I also like
I have a
all
lot of
things.
beliefs that are not justified. And the idea is that the belief that are not justified is part of uncertainty.
Yeah.
But that's not really true, because I am not. So about the fact that in this moment there is I don't know, there is a cat that is working in my garden. It's not that I am uncertain. I have no opinion about it.
Mhm.
Okay, I have simply no opinion. But I am uncertain whether I don't know, my book is good or bad. I'm certain, but I have opinion. I think that is good.
Mhm.
So it's very different. It's a very different situation.
Yeah, but then you don't consider the possibility it wouldn't be good, right?
No, but I want to say is all that is very nice, but it seems that there is a dimension that
That's
is
a dimension
lost.
where the agents would like pick which possibilities they consider as possibilities.
Yeah.
It's like here they are sort of forced to consider all their local state as part of. And that's like, that just gives you all these like closure properties and this kind of implicit flavor of the knowledge that, we struggle with. Because then what you say, if I have an opinion, then I'm cutting out possibilities already.
No, it seems to me that the image,
Or I prefer.
the image should be that you have a possibility of word, and then in fact there are two relations. One that give you the justification, that is what allows you to cut within the word those that are all are true. And then there is another relation that you give you the opinion that what you think that is true or false.
There's-
What do you have an opinion on? So you need
There's
that.
models a bit like that you
So
just,
you complexify a model with two accessibility relation
like
that work in
Mhm.
different way. One include the other, but
most,
not
yeah.
not vice versa.
there's models like that, or in Kripke frames, when you think of set of possible worlds as information state,
Mhm.
then you might think about evidence. So we have like some chosen sets of possible worlds as pieces of evidence, and then you might think that agent have this piece of evidence, but it still doesn't mean that the agent accepts it and believes that the thing it supports is true, but it can mean it. So you can have like evidence structure, we have a belief structure, but we were talking knowledge here. Even like doing belief on simplicial complexes is actually not trivial. It's there's some very much recent work on that, because to give up reflexivity on that is like not easy to see what actually happens, but
Logically speaking, there is a difference between induction and deduction. So you can have a justification based on induction, produce an opinion, and then you can have a justification based on deduction.
Yeah.
That is a
Yeah.
justification. So in some sense, you should distinguish these two if you want to make an analysis of knowledge. Then that is the
yeah, but
is
it's
a
like
is a
more-
very global.
It's
remark.
not general discussion on epistemic like reasoning per se in any
Mhm.
other context. And there's like many competing and like subtly different approaches dealing with evidence, justifications, preferences, like belief. Things like that. Even justification.
Okay.
One more question.
Yeah, sorry, one more question. So it's about, so the reason why you go three valued, right, is because you don't want to say that an agent that has crashed knows everything, right? But because of the semantics that you use, in which the semantic clauses for the knowledge operator is a universal quantifier, where you let to degrade. So in just like standard model logic, you have like alternative semantics in which you don't use like a universal quantifier, but like in neighborhood semantics, for example, you just have a substantial quantifier.
Yeah.
So have you looked at all that possibility?
Not really. I don't know how one would link it to simplicial
Yeah.
complexes that are the prevalent model for distributed computation.
Right.
Psionics, I have no idea. Even like going, like even just weakening this to give up the axiom T is challenging on simplicial complexes. Like the geometry really works nice on these like equivalence-based frames and like whatever I do. Otherwise, I'm not sure how I would turn it into a geometric model. But I can also use it without doing this, and I can say, okay, like let's do it on neighborhood semantics, two-valued and model agents. Why not apply for that? I have this other branch of work when I look at group knowledge for like groups of agents, and the extension of the group can change on possible worlds. So it's not like given, but like in the whole model. Agents might not know who is in the given group, even like they might not know they are in the given group. And then one can like think about like group alive and group dead and like play with this, and it has neighborhood semantics. But I haven't really.
Right, because I mean, also in neighborhood semantics, you have this thing that you don't always have the K axiom, right? So it's really interesting that you see you going sort of non-normal.
Yes.
But you're getting there being like three valued, right? Having this issue with definability. And maybe there's like another route to this that would be
Like it would be normal for the agents who are alive, so I would just pose maybe some closure properties
yeah, maybe something like that.
locally, and yeah. Okay. Cool.
Okay. Let's.
The offices for the student are practically ready. You should already have access.